done at Georgia Tech on understanding video quality using internet measurement.
Let me make sure the mic works. Okay, can people at the back hear me? Yeah. Thanks, Vinod, for the introduction and hosting. My wife is an alum at IISc. She was more jealous, like that I'm getting to visit IISc campus and she's not. But yeah, so today I'll speak about my research. I generally work in the area of internet measurements, and today I'll talk about some of my work that uses network measurement data to understand video performance. So let me give some motivation. Internet video is extensively used for entertainment. Think about watching your favorite Netflix series or watching Cricket World Cup on Hotstar, right? Beyond entertainment, video is also used for remote work, education, and even telehealth. Video is also interesting from a network perspective. It's the largest contributor to the internet traffic. According to a recent report by Ericsson Mobility, 71% of the internet traffic is actually video, and this share is going to grow both in relative and absolute terms in the future. So given these two factors, that is the importance of video in our daily lives, as well as its contribution to the network traffic, it becomes important to understand the network performance of internet video. However, understanding video performance has some challenges. One, video over internet is characterized by complex network dynamics. I'll explain it a little bit now. Let's say a user who wants to watch something over YouTube, they'll connect to the YouTube server over the internet. Now, the YouTube or any content provider can have its own traffic management and content distribution policy. Furthermore, there are networks between the content provider and the user. Due to flattening of internet, assume there's just one network, that's your consumer ISP or internet service provider. Think of it like Reliance, Jio, or Airtel. Now, the ISP can have its own traffic management policy as well. And furthermore, there are interesting complex interactions in the vertical network stack at the user end. For instance, in the case of streaming, there are rate control mechanisms both in the transport and application layer. The second challenge arises based on who is the stakeholder, that is, who wants to measure video performance. Let's say you're an ISP, you have very limited information when it comes to measuring video performance as compared to, say, a content provider. And the third set of challenges arises based on the fact that internet has become so big and is characterized by diverse kind of video applications, including both video conferencing and streaming. Furthermore, at the user side, the networks are ginormous, so the number of users for which you have to infer performance can be large, and these users are characterized by diverse streaming and network contexts. So my work tries to address these challenges by specifically building. Yeah.
So to what extent do it's like Akamai have a role to play here? I mean, do they also cache video content?
They distribute video content. Yeah. So CDNs are heavily used for distributing video content. Yeah. So So my work tries to address some of these challenges by helping different stakeholders understand video performance, and I do this by building measurement methods and systems. More broadly, I'm interested in building measurement methods and systems to help different stakeholders understand internet performance and accessibility. Concretely, my work maps to 3 threads. One is measuring the networks themselves. So trying to understand who has internet access and how good quality of that access it is. Then it's the next 2 threads, they measure application performance that run over the networks. So mostly focusing on video. And one thread helps ISPs understand video performance using passive measurements. And the other thread is helping application providers understand network dynamics of video content or video applications, and that can help in a more network-centric and data-driven application design. So my work has been published both in networking conferences as well as multimedia and telecom policy conferences. Specifically, the work on understanding the digital divide, measuring the digital divide, has had significant community engagement. This is work that I started in my PhD and also continuing during my postdoc. And the work on helping ISPs understand video performance was in collaboration with the real ISP. So the methods and systems we propose are deployed in the ISP's network. So in today's talk, I'm mostly going to focus on the work that helps understand video performance. Specifically, I'll talk about one method that we developed that uses passive measurements to infer video quality of experience. Then I'm going to talk about a measurement study that we did that looked at performance and utilization of popular video conferencing application. And in the last 10 minutes, I'm just going to talk about my future research vision. So let's start with the first topic. So just to give some context, so quality of experience is a measure that is used to characterize user satisfaction when they use an internet application. Right? Here's a definition of quality of experience by ITU. It's a standardization body. So interpreted literally, quality of experience is a very subjective measure, which makes it challenging to infer at scale. So as a result, objective metrics are often used to approximate quality of experience. So let's look at what these objective metrics are in context of video streaming. So most video over the internet is streamed using a protocol called HTTP adaptive streaming. And I'll talk about how the protocol works a little bit later in the talk. But the idea is that the player adapts the video quality to match the network condition. And this is done to ensure an uninterrupted video playback. Because of this kind of streaming behavior, the quality of experience can be approximated by the following objective metrics. The first is average bitrate, which is really the average video quality during a session. Second is rebuffering ratio, which is the proportion of time video stalled. Then is the third is bitrate switches, which is number of times the video quality changed. So you would want to minimize these variations in video quality. And the fourth is the startup time. It's the amount of time it took to begin playing the video since you first press the play button. So now the question obviously is like, do these metrics matter? Here's a study by Mux which shows that having one or more stall or rebuffering events during a session can reduce user engagement by almost 40%. Now, given internet is an eyeball economy, lost engagement translates to lost revenue. So naturally, all stakeholders in the video streaming delivery ecosystem care about optimizing these QoE metrics. One might still ask, like, do ISPs care about rebuffering or what's the video quality, right? So here's a survey which asked users how likely are they to blame different entities for QoE impairment issues. You can see that ISPs get the blame majority of times. So naturally, ISPs would like to have an in-depth understanding of video QoE over their network, and this can essentially help them in an efficient network management and capacity planning. However, understanding video QoE is challenging for ISPs. Unlike content providers, ISPs do not have access to the end user application, the device, or the server, right? All they have access to is the network bytes that descend from client to server and back from server to client. So ISPs are constrained to rely on the measurements of this traffic to infer QoE, these measurements are usually called passive measurements. However, using these passive measurements to estimate QoE is also not trivial. Let's look at some baseline approaches, right? One simple thing could be to use some standard network quality of service metrics, which most ISPs monitor, like things like throughput of a flow or losses observed during a flow. So the idea could be like you could say like low throughput translates to low QoE, right? But this is not enough for HTTP-based adaptive streaming, and this is because the relationship between the quality of service metrics and the application layer quality of experience metrics can be complex. And this is because of two reasons. One is the use of bitrate adaptation. So the same amount of throughput can mean a large amount of low quality video content or a small amount of high video quality content. And then the other is the use of video buffer, which is the video that's downloaded but it's not played. So depending on how much video is in the buffer, you can be robust to small network variation. So given this approach it would not work, the other idea could be to look at application level headers, use something called deep packet inspection. So you could look at essentially, let's say a packet is composed of IP transport and application layer headers. So you could basically inspect the headers in this layer and try to make some guesses around QoE. Now, given the fact that an increasing amount of video traffic or any traffic on internet is end-to-end encrypted, ISPs lose visibility into this application layer. All they have visibility is into the IP, the network and the transport layer. So my work basically tries to address these challenges, and we build a method that basically addresses these challenges and uses passive measurements to estimate video QoE. So let's look at what the design space for QoE estimation methods could be. The most existing work, they formulate this QoE estimation problem as a supervised machine learning problem, and the idea is you collect a sample of network data as well as some ground truth QoE data and use it to train your ML models, and then which later can be used in real world for predicting QoE, right? So this would work if ISPs have access to ground truth QoE data. But remember that ISPs need to estimate QoE for a wide variety of streaming services for different kinds of user platforms and network conditions, which makes it challenging to get ground truth data for such conditions. So given this challenge, we consider, is there an alternate approach? Specifically consider this approach which we term as session modeling. Is can you utilize the network properties of the underlying streaming protocol to model a video session? So let me give you an example of what I mean. So consider a hypothetical scenario where you knew, for example, a content provider always encoded their videos at 1 megabits per second, right? So just by knowing this information about the streaming protocol, you can tell a lot about what's the average bit rate switches will be 0, and then you can also monitor the traffic to estimate rebuffering, right? So an advantage of using this kind of approach is that you require minimal ground truth QoE, right? Then it can also generalize across streaming and different streaming and networking contexts as long as the underlying streaming protocols are similar. And then it also provides an explainable QoE inference, which is generally preferred by network operators. So given the advantage of designing a session modeling based approach, we ask, can we design such approaches to infer QoE for video streaming?
One question.
Yes.
Can you go back to the previous one?
Yes.
So how would you model the rest of the network over here? Particular method. I mean, you have to model congestion in the rest of the network and so on, right?
So you're basically looking at the network traffic during the session, right? So you have basically what happened, right? So you're not trying to predict what is going to happen in the future, right?
So it's live. It's not like a model that you construct and then.
Yeah, you're not going to predict what is happening in the future, but what is things like maybe trying to what is the buffer at currently the buffer occupancy at the client. So those kinds of questions you're asking, or so far, what is the video quality that the client experiences?
Okay.
Yeah. Yeah. So we basically try to design session modeling based approaches, and we first consider the case when the traffic is unencrypted. We develop an approach called Mimic that uses basically HTTP transactions that you can log for unencrypted traffic. We validate this approach using data from real-world ISP. And then we relax this assumption that the traffic is unencrypted and design eMimic, which uses packet traces to infer the QoE metrics. And in this talk, I'm just going to talk about the second piece of work, this eMimic. So I'm good, thanks. Given that these session modeling based approaches rely on the streaming protocol properties, so it's a good time. I'll tell you about how HTTP adaptive streaming works. So the idea in HTTP adaptive streaming is you divide the video into smaller chunks, and then you encode each chunk at different qualities. So think of, say, a Game of Thrones episode, right? So it's a 1 hour episode. It'll be divided into 4-second chunks, and then you encode into 240p, 360p, and 720p, and so on, right? And then all the logic to stream the content, since it's stored on a HTTP server, which is a stateless server, so it relies on the player side. So the player basically starts downloading these chunks one by one. So to download the first chunk, it will send a GET request, receive the response, and then once that chunk has been downloaded, it will send another GET request for the next chunk, and so on. So if you really think about an HTTP adaptive streaming session, you can model it as a sequence of video chunk downloads. And if you track these video chunk downloads on the network, you can essentially estimate the QoE metrics. So that's what we try to do in eMimic. So we use packet traces collected on the network to model. Yeah.
So this chunk isn't like equivalent to a max size of a packet?
No, so it's like basically fixed size duration. It's more than a single packet. So for example, I mean, Netflix uses 4 seconds chunks, so it's a lot of packets. Yeah. And it's typically the chunk duration is, I mean, most services they use a single chunk duration, but it can vary across services.
Who decides which of the chunks to send? I mean, which of the
So the player decides it based on its some notion of what is the observed bandwidth conditions.
It asks only for that kind of.
Yeah, yeah. It says like, oh, I want the first chunk at low quality, the second chunk at high quality. Yeah. So the key idea in eMimic is that we model a session as sequence of chunk downloads, and you track these chunk downloads by logging the packet traces on the network. So there are some key challenges in tracking video chunks from packet traces. The first thing is basically these chunk downloads are essentially HTTP transactions, right? So the first challenge is like you need to reconstruct HTTP transactions from packet traces, which I mean basically we needed to track these chunk downloads, right? So once you do that, in these HTTP transactions, there will be transactions corresponding to different kinds of media types. There will be audio data, there will be metadata. So you need to isolate video chunks from these other kinds of data. Once you do that, you still need to estimate the bitrate, average bitrate of each chunk. And in this basically you need to estimate the QoE metric, bitrate and number of switches, right? So now
Just you drop, I think when I got dropped.
oh, even I got dropped. Oh yeah, yeah. I need to share again, right? Oh, my network. Oh.
share your slide.
Yeah, I did that. Can you see it now? Yeah. Let me try the screen sharing. It's
Visible.
it should be visible. Oh yeah, okay. I thought you were saying like the border is not there, so it's not shared. Okay. Yeah, so basically, we are considering HTTPS. So you still have HTTP transactions, but from the net. Let me just. Okay, let's see if there's any echo. Okay, so now yeah. So basically, from the network, those transactions are not visible. So yeah, but there's still HTTP transactions. So that's what we're trying to reconstruct because they're not visible from unencrypted traffic.
And this is running on device or on ISP?
On the ISP side. So imagine ISP is sending all the packets, so it's logging these.
The data is encrypted. Can ISP detect what is the bit rate or what is the media type?
So all they've access. So basically, data is essentially packets, right? So they can still tell. I mean, the IP headers and the transport layer headers are unencrypted. So you can tell what's the size of the packet, and you can tell the source and destination and timings of those packets. And yeah.
But still, I'm not convinced. Like just looking at the packet header, you can tell what is the bit rate or.
Yeah, that's what we are going to estimate basically. Like that's a challenge, right? You cannot do that just by looking at the packet. Yeah. So the first thing we do is reconstruct HTTP transaction, and there we utilize this directionality property of HTTP transaction. Basically, in an HTTP transaction, you have data. You have a GET request where the data flows from client to server. This is followed by response where the data flows from server to client, right? So essentially, if you look at the source IP of your traffic, you can use that to mark boundaries of HTTP transactions. And if you do that, you'll basically have, for a single session, you'll have a sequence of HTTP transactions along with their estimated size, because you have packet sizes. So you can just add them up. And then also the timings, right? So you know the start, and then you also know the last packet in the downlink direction. So that's your start and the end of transaction, right? So once you do that, you now have a sequence of transactions. So to identify the media type, so identify video from these transactions, we use the size of the reconstructed transactions to do that. So here's an example what I mean. So here's the size distribution for different kinds of media types for a sample service. So you can see that metadata is very small in size. It's because it's mostly text. Audio data is also small in size, and it's also very consistent in size because it's audio typically is constant bitrate encoded. And then once you identify what is metadata and audio, you can say rest of it is video. Well, this will work in most cases, except for a small number of cases where the video content can have overlapping sizes with the audio content. So to avoid misclassifying those video chunks as audio, we also use another insight that the amount of audio and video data downloaded during a session would be similar. The duration of the data would be similar. So we track the audio and video buffer to avoid some misclassification. Once we do that, we basically have a sequence of video chunks. Then we estimate the chunk bitrate. Now, an obvious insight is you can use the size of the chunks to estimate the bitrate with an intuition that higher quality chunks would have larger size, right? You can see this is not enough. For example, in this case, this shows the size distribution for different bitrate, average bitrate level or video quality levels. You can see that the sizes basically they can overlap, and this happens because video is variable bitrate encoded. So depending on the complexity of the scene, so you may have especially with consecutive bitrate levels, you may have a lot of overlap, right? So we use additional insight that
Bitrate of video or a bitrate of the
of a single chunk. So this is so basically the chunks are encoded at a different average bitrate levels. So for example, in this case, each chunk was encoded at 7 different levels. So, and then we look at the size, but the size of a specific chunk would depend on the complexity of the underlying video, right? So as a result, you can see that, and given that it's variable bitrate encoded, you see variability in sizes, and this is just plotting those.
So, this is a bitrate of the video, not of the packet bitrate, right?
Yeah, this is chunk bitrate, video chunks. So you have video divided into chunks. So this is showing the distribution of those chunk bit, size distribution of those for a specific bitrate level. Yeah, packet bitrate doesn't make sense, right? I mean, like if a packet belongs to a specific chunk, you can estimate that bitrate. Yeah, so all packets belonging to the same chunk would have the same. I mean, that's the chunk bitrate. Right? Okay. So we basically use additional insight that players typically switch bitrate when there are changes in the network throughput. That's the whole idea of bitrate adaptation, right? So we also log the observed throughput on the network, and then if there significant variations in throughput along with chunk size variations, we detect basically bitrate switches. So once we do that, we have a sequence of video chunks along with their estimated timings and their estimated bit rate. So we can estimate the key quality of experience metrics in the following way. So average bit rate is simply.
How do you, maybe I missed it, how do you know what packets belong to the same chunk?
Oh, so we consider the HTTP transactions, right? So packets are grouped into transactions, right? So basically this is, let's say this is a single HTTP transaction, right? So you have multiple packets that are being transmitted over here. So by looking at the direction of the HTTP, direction of the traffic. So basically, let's say you have two client and a server, right? So you can tell what traffic is if the traffic is originating from the client or server, right? You can tell that's upstream or downstream, right? So
Are you working at the HTTP level or at a lower?
I'm logging the network traffic on and then I'm just looking at the IP headers and the TCP headers.
You're not looking at the TCP level. You're looking at the protocol level.
No, I'm looking at the IP and the TCP. So I'm mostly looking at the source IP. TCP headers are used for accounting for retransmissions and those kinds of things. To understand like what is an ACK and what is the data packet.
I don't understand how you know where a chunk ends from another chunk.
Yeah, so basically, okay, so basically when you download a chunk, you send a GET request. You say like I want to download.
Each chunk has a GET request.
Yes. Yes, that's the assumption here, and that's followed by most services except YouTube, which does chunk batching, which can download multiple chunks and in an adaptive manner. So this kind of method would not work for that, but most services they download one chunk at a time.
And so the idea is to estimate the chunk size and then from that the bit rate. Is it?
Yes.
Because you have the graph relating chunk size and bit rate.
Yeah, I mean basically, yeah. So you have this notion
this graph is empirical. It's not that ongoing session, but it's
it's sort of
historical.
Historical data. So we are not just using the size, but also this idea that throughput variations would lead to bitrate adaptation. Otherwise, players would not adapt bitrate. So just by looking at size, you might basically a chunk from 1000 kbps would have similar size as 650 kbps. So just using size is not enough. So we look at both of those things. Yeah, but what we assume is we know what are the average bitrate levels, and most, like for example, Hulu would encode their video at 7 bitrate levels. Netflix would encode at 5 bitrate levels. YouTube and so on. Okay, so yeah, so once we do that, basically we can estimate average bitrate by just taking the average of chunk bitrates. Bitrate switches also, you can just look at consecutive chunks and see how many times bitrate switch. And then to estimate rebuffering ratio, we basically model the buffer occupancy. So essentially, there are two things happening at the player side. Once a chunk gets downloaded, the buffer increases by the duration of the chunk, and then the buffer is also getting depleted as the content is being played on the screen. So assuming 1 second of content every second, so you can track both of these to estimate where rebuffering occurs. Yeah. So basically, so you know when the chunks are getting downloaded, right? So you have the timings of that, and so every chunk, let's say, is 4 seconds. So you know, like, okay, this chunk got downloaded, so the buffer occupancy must have increased by 4 seconds, right? But then let's say the chunk got downloaded in 2 seconds, right? So in that time, 2 seconds of the video must have been played. So now, like, you add 2 more seconds in your buffer, like whatever your buffer occupancy was before this chunk was downloaded. Now at the end of this chunk download, now it must be +2.
So 2 seconds of happening. Same time, some packets are also coming.
So to decode the I mean, you need to decode the whole chunk. So you'll only decode it once the full chunk has been downloaded. So it's not like, so there's no partial decoding.
So how average bitrate is like coming into
For rebuffering ratio, average bitrate is, you need the timing information basically. Yeah.
let's say for 210 average bitrate, my distribution of the packets may be different, right? So are you also considering that part? Means in one case it may be one burst period and there is no packet. Maybe you get some average bitrate, and in another case you may get like nicely distributed packets, and in that case also you may get the same average bitrate as a bursty plus ideal case. So are you differentiating between these two?
So you're saying, like, basically the last packet of the transaction can be so the average of 2 chunk downloads can be the same, and but
the pattern is different. The incoming how the packets arrive, that pattern is different.
Yeah, so it's basically like different streaming services could have different shaping, or like
something like that.
Yeah, I think what we are looking at is basically 2 signals. One is the size, and then also the throughput, right? So the idea is like like a lot of chunks would probably have similar bit rate during the session. So if you track the average sizes, so you can use it to detect what the bit rate is across, unless there's a change in the network throughput. So the idea is like one of these signals would help you not switch things too much. So it sort of creates this hysteresis effect to create, yeah. Okay, so now I'll just talk about how we evaluate our setup. So we use an automated browser-based framework to get some packet traces along with the ground truth QoE data for validation, and we do this for 2 streaming services and collect almost 1,000 sessions for each service streamed under various network conditions. So now I'll show you some accuracy metrics. So one thing we do in QoE estimation, one intermediate step we do is this media classification of transactions, right? So we classify them into audio and video. So here's one result showing that the confusion metrics, where you use only the size of the reconstructed transactions, and you can see the accuracy is generally high, the numbers on the diagonal, and if you also add this buffer tracking inside, the accuracy improves slightly, right? And this is the result shows the accuracy of estimating average bit rate. So the x-axis here is the signed difference between what is the actual and the estimated bit rate. So you can see we can estimate average bit rate within 80%, within 100 kilobits per second for 80% of the sessions, most for most streaming services, the bitrate levels, they differ more than 100 kilobits per second. So it's a reasonable granularity. Yeah.
Question regarding the you separated out the audio traffic for the text traffic for the
Yes.
But given the total amount of data transmitted on the audio and the meta channels is so small, I would imagine that even if you compute your bit rates, none of your classification complexity, you get very close to the original to this data. Right?
Yes. I think that's a good insight. But like, okay. So one thing I want to clarify: this is not. I mean, this seems like average bitrate, but this is like really capturing the average video quality. So it's not just looking at the sizes and just averaging the sizes, because I mean the sizes, because the variable bitrate can differ, right? The other, yeah, but you're right. So average bitrate is slightly easier problem than estimating the other things.
Yeah. So my question is, like, do you have data that actually eliminates your separation task and just says, I don't care about the traffic separation. I'm just going to use the packet information and I plot it on top of this curve.
Okay.
And how close is it to your actual?
That's a good point. We didn't do that, but we evaluated our approach with an ML, like let's say you just use simple machine learning based approach, and there we found that those approaches do pretty well in estimating bitrate because it's an easier problem.
I guess the one thing that I kind of miss is the connection to, like, what would be measured, like what does it lead to from an end user's perspective or from an ISP's perspective?
So from an ISP's perspective, I mean, they could basically use this information to do network management. One, they could identify, for example, locations in the network where there's persistent QoE, where there are persistent QoE issues, right?
Okay, so I assume that you will talk about some solutions that you take this data to some end conclusion. Is that right?
No, not in this talk.
Oh, okay.
Yeah. Okay, so then I'm this result basically what we did was we compared the accuracy in estimating rebuffering ratio with an ML based approach that was proposed in our related work. So the idea is we classify rebuffering ratio into 0, mild, and high. And for ML based approach, you use some data for training and test it on the rest of the data. And so this is the accuracy numbers on the test data. So left hand side is the confusion metrics for our approach, and the right hand side is the ML baseline. So you can see that we can estimate high and low rebuffering ratio sessions with much higher accuracy, and that too without any training overhead, right? Because the session modeling based approach doesn't rely data to train the models. Okay, so yeah. So this was an IMC paper in 2016 that was proposed, and it used some statistics calculated on the flow, network flow, like throughput, average median of throughput, losses, RTTs, and stuff like that.
I mean, what exactly are they using?
They're using random forest. Yeah, so the ML models are basically classic ML models, and what they found was random forests give high accuracy.
So your goal is to classify the three classes.
Yeah. In this way, yeah.
So why three classes? Is there any?
The intuition, I think, this comes from the what could be a possible use case for an operator if they want to. I mean, they might want to say I want to minimize my low rebuffering ratio sessions, that kind of stuff. Yeah, but you could use. I mean that's what the paper did. So we just replicated it, but you could do more regression and those kind of classification.
To kind of follow up.
Yeah.
The place where the approach seems to have most difficulty in the confusion matrix is the mild data, right?
Yeah.
Or mid, I can't read mild data.
Yeah, mild.
And so, do you have an insight into why you particularly fail in that category?
Yeah, that's a good question. We didn't explicitly explore why, but there's some intuitions why you could fail in that. Like one is that so for example, you see we end up basically classifying mild into 0 rebuffering ratio sessions, right? So the idea is you're observing things on the network layer, but there are additional delays at the from where you're observing to to the client side there on the application layer stack, right? And then the kind of streaming model we assume that once a chunk is downloaded, it'll be immediately played. So let's say the buffer is low. Sometimes the streaming service can choose to not play the content and wait for a little bit more and those kinds of things. So essentially the idea is like there might be some application layer delays which are hard to account for from the network data.
What does rebuffering have to do with bit rate?
So this is just a different QoE metric that operators are interested in. Right? Like basically stalls impact. I mean, let's say you were watching YouTube session, right, and you've had a lot of stalls. You'll stop watching it, right? So, and then you may want to say like, oh, my Wi-Fi is crappy, or like the network here is crappy. So
What is whose occurrence is more like 0 mile or highest? So which occurs most frequently?
More, you mean in the real world case?
Yes.
I mean, yeah, think about like more streaming sessions, and depend on the particular network and how you're streaming it, but most network conditions are usually fine. There are a small proportion where the network is congested, like where there's some transient congestion in the network, you see more of these. So yeah, essentially, yeah, the data is generally skewed towards 0 rebuffering ratio session, like in the real world as well.
So when you say it is 2 to 0, it's not exactly 0. So
I mean, like basically 0. So it's exactly 0.
So, my opinion, most of the data lies in the mild category because getting 0 is very difficult.
No, so you can get 0 when you differentiate the initial buffering you did, the startup time. So from the rest of the session. So typically, players or basically content providers treat these as two different things, right? So initial rebuffering users have different tolerance than once you start playing the content, and then you observe a stall. So. Yeah, we had it in the paper. I don't remember the number. It might be like that. It also depended on the specific network conditions we use. So it's probably not representative of real world network conditions.
This you are talking about will be depending on the state or the country. Right? There are
Yeah.
internet generally is bad.
Yeah, you're right. Yeah.
So this, I mean, a place where internet is average, like suppose, and then your method might be falling under the mild category all the time. If that is the case, it might be an issue.
Yeah. That's an interesting point. Yeah. So, but remember that our method is not doing categorical. We can actually do exact estimations. So you could also calibrate things accordingly later on, like depending on what you're trying to use it for, right? I mean, basically, you can say like how many sessions where the buffer was less than 1 second. So I'm not looking at cases where the buffer was exactly 0, but buffer was 1 second, right? So you could do some of those calibrations. Okay. So in summary, so in this set of work, like I told you about like one of the methods that we develop, but I've done some more work in this area, looking at some system challenges of deploying this approach, say in a real world network. So we particularly present the design of an end-to-end QoE inference system for an LTE network, and then we also looked at when you have more coarse-grained data and not packet-level data, which can be challenging to collect at network-wide scale. How do you do inference in those cases? So now I'm going to talk about the next piece of work, which is sort of a measurement study of popular video conferencing applications. So one thing before starting streaming, that is YouTube, Netflix, is very different from conferencing like Teams or Zoom. In streaming, you have a client-server model. In conferencing, you have two end users, which either connect directly over the internet. It's called peer-to-peer, or they can connect using a relay server provided by the content provider, the conferencing application, right? Another difference in between streaming and conferencing is like in streaming the video is pre-encoded and stored on a server. In conferencing there's real-time encoding, and because of those reasons, yeah.
I just had two questions about the previous one.
Oh yeah, sure.
So, sorry. So, lower bitrate or buffering could happen due to other reasons also, like a poor Wi-Fi connection inside my home.
Yeah.
So how would the ISP know whether they are to blame or whether this?
So yeah, so that's
my home Wi-Fi router is
right. So what you're estimating is basically with these methods is end-to-end QA, but then there's like a next step where you get like, let's say you observe a QA issue, right? Can you say like, oh, it's because of an issue in my network, right? There you can pull data from say.
All users on the same.
Yeah. So one simple thing could be like, let's say you're a cellular network and one user in your base station had QoE issues. Like you could try to look at say cell signal for that particular user around that time and see, oh, it might be an issue of the cell signal, or there's so many users on that base station, so it might be because of that. Or if that's not the case, you can say, oh, it's not my network, but something else.
The other thing was. So if they detect an issue, what are they supposed to do? What action are they?
Yeah. So I think that's something that I'm still exploring. But the idea is like one is you could just do sort of long-term capacity provisioning. So I'll tell you like one thing like AT&T is interested in like which cell sites they should upgrade, and there are a lot of you get a lot of cell sites, but how do you prioritize those cell sites and those kinds of things? So currently the methods are mostly QoS based, which may not work. I mean, which may not reflect user performance. So the other is like more real-time resource allocation. You could think about, let's say there are two users, with one is having 1 second of buffer, the other is 10 seconds. You can maybe give more bandwidth for now to this user, or you could do routing in a different way. If you observe there's some congestion on interconnect and those kinds. Those are like some real-time changes you can make. Yeah.
Live streaming, like it is equivalent to video streaming or video conferencing?
Yeah. So live streaming is a nice case. So for scalable live streaming, it's done in a similar fashion as video streaming, where you encode, say your data is 2-second chunks or 1 second chunks, and that's why you'll see like if you're watching, say on like the match in the field versus on your TV, there's a delay because of this kind of this kind of streaming mechanism, and this is to achieve scale basically. But if there's small number of users, then you may fall in this kind of category.
There is some sort of consortium between the ISPs and these content providers, and they directly share the users.
That's
how does that?
Yeah, that's an interesting proposition. One, it has like a lot of non-technical challenges, like you're asking Netflix to share information about what users. Yeah, but there are also like one more challenge is like even if you get that information, how do you detect what happened? Like was it like you still need to collect additional data on your network to do some diagnosing and stuff, right? So you still need to like one and also like. What Netflix would give you is like, okay, this user saw rebuffering, right? But then you need to either store, okay, like this user at this time used this path, right? Use this network. So you still need to do some more work. So it's not like as if you get that data and that makes life easier. So monitoring within the network is like more intuitive step in that case.
In a network-wide measurement, getting packet level data, this packet level data might be.
It is challenging, yeah. Yes.
What kind of course level data?
So I mean, you can still get some aggregates over, like you can one you can get depends on what kind of monitoring framework you assume. Like nowadays, like people have this flexible in-network monitoring framework, so you can have you can monitor and calculate actually packet level stuff and do some in-network compute and store more aggregate information. So that is like one way where you can do some flexible monitoring. The other is like, the the kind of data that we worked with was basically TLS transactions at the level of like which has multiple HTTP transactions within it. So the interesting issue is like most ISPs they get these monitoring equipment from vendors, so they don't really have I mean, in theory they can, but in practice, like changing, they don't really have control on what they can get. Like tomorrow, if the vendor decides to give you some information, they'll get it, but otherwise not, right? So for the particular network that I was working in, we had access to these TLS transaction data, but let's say you were a vendor, then you could maybe have more sophisticated monitoring schemes as well.
There are like demand for open source.
There are startups in this area now. Yeah. So I mean, there is a demand basically. I mean, if you develop something that works at scale and present to ISPs would certainly be interested. We were talking to a few startups, but the fact that we did this work with ISP is like hard to. Okay, so now I'll briefly talk about this measurement study that we did to understand video conferencing application. As I was saying, was basically these conferencing applications are different from streaming applications in terms of their network and application protocols. Basically, the conferencing applications I would argue are more complex because they have to do a lot of heavy lifting in the application itself. So, for instance, most conferencing applications use UDP as a transport layer protocol. And if you know that UDP doesn't give you any error recovery or congestion control mechanisms. So these mechanisms are then implemented in the application layer using a protocol called real-time transport protocol. And then there are also encoding mechanisms that the application needs to implement, which are again tightly coupled with these congestion control and error recovery mechanisms. The other thing is most video conferencing applications use relay to transmit data, especially for more than two people, when there are more than two people in the call. So and the kind of relay mechanisms each application implements, are really application specific. So as a result, you find proprietary and different implementations across VCAs, which are essentially black box. So what we do in this work is like sort of a systematic study of network dynamics of these modern VCAs. And this work was especially, I mean, we did this after pandemic when people really started using VCAs very heavily. So we did this empirical study on three popular video conferencing applications, that's Zoom, Meet, and Teams. And the kind of questions we looked at was like, what is the consumption of these VCAs? And how these VCAs adapt to low network, poor network conditions, and then how do you like the way you use the VCA? How does that impact your network consumption? And then we look at how things like network disruptions and competing traffic impact like these VCAs, how do they respond to these conditions? Now, these questions have wider implications. The first three set of questions, they have implications on how you manage network, also on broadband policy. And the next set of questions, they have implications on application design. Now, to study these questions, to answer these questions, we basically had a in-lab test methodology where we basically had VCAs calls and collected some traffic around these calls. Now the first challenge there is that initiating these VCA calls require a lot of user interaction. So what we did was we developed an automated experimentation framework that initiated these calls, and we also made it modular so you can easily extend it to other VCAs. Then to ensure consistency across experiments, we used a pre-encoded video and essentially a talking head video to emulate a real world call. And then to isolate the effect of specific network factors, we basically shaped links in lab and then try to see what is the effect of different network conditions on VCA performance. And the other challenge was basically this this VCA, I mean, this path may seem symmetric, but because of the use of a relay server, uh, uh, any impairments in this path are different for impairments in this path. So we basically looked at both kinds of impairments separately and try to explain why the differences occur. So in this talk, I'll just explain the findings from two of the questions. So that one is impact of network disruptions and competing traffic.
Video are same
Across experiments.
Saying the same video and they're just saying the same video.
Yeah. So yeah, to understand the impact of network disruption, we basically had a two-person call setup, and essentially we introduced a network disruption 60 seconds into the call, which lasted for 30 seconds, and then the cap was restored, and then we look at how basically VCS respond to these network disruptions. Here's the recovery patterns for one single call for the three different VCAs. So the y-axis is the utilization, and you can see that during the interruption, of course, the utilization reduced. It was the bandwidth was capped at 250 kbps, and then the VCAs start recovering from these from this disruption. And the recovery pattern is very different. Zoom, for example, has the sort of almost like a linear recovery, and then the bandwidth is stable. And the interesting fact is that it doesn't stop at its nominal utilization. It goes all the way up. Like there's some sort of bandwidth probing, and we found that, I mean, you can imagine this sort of bandwidth probing can impact other competing applications. Like let's say you were watching Netflix right now, this may end up eating the bandwidth, and we found that to be the case. Teams and Meet, on the other hand, have very similar recovery pattern. The recovery is slow in the beginning, and then it sort of ramps up. So if you think of, like, it's very similar to, say, a TCP cubic kind of congestion control mechanism. But the idea is, like, these VCAs, they implement different congestion control mechanisms, and then we looked at how that impacts user performance. So to do that, we look at specifically the time to recovery, that the time it takes to get back to the nominal utilization before the disruption. And here's the time to recovery for different kinds of disruptions. Whether, here the different disruption was 250 kbps and so on. So you can say the time to recovery is high. For Teams, it's almost 25 seconds in all disruptions, and for Zoom, it's like almost 50 seconds for very severe disruption. And also, the time to recovery differs based on where the disruption is, whether it's between the client to the server, because most of all of these VCAs, they use a relay server. So whether the disruption is in the uplink, that is client to server, or downlink between server to client, you can see that the time to recovery is much smaller in downlink disruptions for Meet and Zoom, but for Teams, they're almost consistent. And then we explain in the paper why that's the case. But essentially, a combination of how VCAs encode video and what kind of mechanisms the relay server uses. We next look at the impact of competition. So we use a classic dumbbell topology where we have two VCA clients sharing a bottleneck link. So the idea is you have one VCA call happening, and then 30 seconds into the call, another call is initiated. That's a competing client join, and then we look at how this bottleneck link is shared in those the 2 minutes where the competition is happening. So here's a result where the incumbent client is a Zoom application. So imagine you're watching a Zoom application. You're doing a Zoom call, and then either a Teams client join or Meet client join or Zoom client joins, and y-axis is the share of the link. So ideally 0.5 is the fair share of the link. You can see Zoom is very aggressive, even to a new Zoom application. It basically ends up hogging the bandwidth. In contrast, Teams is very passive. It basically gives away bandwidth, especially to a Zoom client, right? So we also looked at other, competition with other kinds of application, including TCP flow, and also like videos that are watched, basically streaming videos watched over TCP flows, and we found that like there's a lot of uh, there's a lot of you know there's the idea to design congestion control mechanisms that are fair for TCP world, but in the VCA world, the congestion control mechanisms are not simply fair to a TCP or to even other VCA flows. So as I mentioned, we looked at other aspects in this study, including the performance and consumption, the source consumption of VCAs under constrained link capacities as well as client modalities, and we found that there are significant differences across these VCAs, and try to explain why that's the case.
When you talk about network disruptions and the time to recover or
Yeah.
recover, are you still looking at only the video streams and then making your decisions, or are you also looking at...
So this work we looked at video. There's actually a lot of related work that has looked at audio streams, so we just focus on video in our work.
Why is that important? Video conferencing?
Yeah, voice is really important. Yeah. So yeah, we didn't look at it in this work, but there's related work that does that. Okay, so now in the next 10 minutes, I'll quickly explain like my plans for future research. So I would argue that internet is no more a luxury, but it's a necessity. So my vision is to facilitate a high quality and low cost internet access for all. Let me contextualize it a little bit more. So here's a figure that shows internet connectivity in India. The data is from World Bank, and it's until only 2020. I'm sure the numbers have improved in the last 2 years, but the question is, how do you go from here to connecting everybody? And then also looking at quality of this access. Here the internet speeds reported by Ookla, and the question is, how do you increase internet speeds, and then also look at measures beyond speed, more meaningful measures that capture user performance. Right. So to do this, given that how big internet and complex it has become, you need to make data-driven decisions. Different stakeholders need to make data-driven decisions, and that's where I want to help these stakeholders make data-driven decisions to improve internet performance. Specifically, I'm interested in these 3 areas. The first is basically understanding where internet is and where it is not, and then helping in mitigating it. So this is, as I was mentioning, this is work that I've started during the later part of PhD and continuing it. So in most of the current work, we have looked at measuring access and its quality in an accurate manner. And then we've also looked at dimensions beyond access, including adoption and digital literacy. So just to give a flavor of things that we've done. In one set of work, we've looked at what existing data sets talk about internet access. This is done in context of the US. So we in one work, we analyze different data sets that report mobile broadband coverage, including data sets that government reports, which is data collected from ISPs, and then data sets that are collected by taking user level measurements. And what we found was that there are significant disagreements between what the government, basically the ISP reported data and the user level data, especially in rural and tribal regions. In other set of work, which was done in collaboration with the city of Chicago, we looked at internet adoption variability across neighborhoods in Chicago using existing data sets, and found that there's significant disparities in internet adoption. And this has to do with the history of Chicago. Then we also look at beyond this answering binary question of internet, is internet there or not, but how good quality internet is. So for this, we have designed a network measurement platform which we are calling Netrix, which is essentially a Raspberry Pi based setup consisting of network measurements that are deployed on this Pi, and then you can plug this on in your router, and then it will collect continual measurements. So we developed Netrix as an open source platform, and have deployed this in around 100 households in Chicago, and we are looking at more deployments, also collaborating with ISPs for these kinds of deployments, and we've been collecting data almost for a year. So just to give a flavor of kind of work we are doing with this data, one is like we are trying to compare internet performance across neighborhoods, or across geographies. Is geography A getting better performance than geography B? The other work we are doing is working on the measurement methods and tools themselves. So in this work, we analyze two popular speed test tools, and then which are basically designed in a different manner, and then we try to see when these tools differ, and how why do these tools differ. So we do both some in-lab experiments as well as analyze the data collected from these deployments. Okay, so in future, I mean, I want to continue working on these problems, as well as also work towards mitigating internet inequity. So community ISPs, for example, are one possible ways to provide connectivity in areas where ISPs do not have incentives, or the internet cost is very high. So one set of work we are actually looking at is like, can you help facilitate deployment of these community networks? So oftentimes these community networks, to save costs, they're oftentimes wireless based, and sometimes use niche wireless technologies. So we are helping operators understand the reliability of such technologies, and then also one challenge what we're seeing is that that's an impediment in deployment of these community networks is the huge learning curve for network management. So now we are exploring how you can make network management more accessible for non-experts. Then the other thread that I want to focus on is is basically related to this inference of QoE for ISPs. Now, as applications over the internet are becoming more complex, the traditional QoS metrics are not necessarily sufficient to network management. So can you do a more QoE-aware network management where you take user performance as a center thing and try to optimize it? So there we are looking at problems of how do you do QoE inference in an accurate manner for all kinds of applications and in a scalable manner. And then there are questions that we alluded to earlier as well. Like once you have this QoE information, you need to basically do some sort of troubleshooting to understand, whether the issues are occurring inside the network or outside the network, and then you need to take appropriate decisions based on that to do network management. And then this is a more recent thread that I want to work on. In my work as well, we've used machine learning for different kinds of network analytics tasks, but there's a huge gap between what you develop in lab versus what it'll take to make it work in real world. So I want to work towards bridging this gap. So some specific problems that I'm interested in there are like, so how do you collect, for example, data for different kinds of network analytics tasks? So designing systems for that, especially modular experimentation frameworks. Then in a lot of these network analytics tasks, basically you use handcrafted features. So can you have more flexible and generalizable representation of network data? And then there are always questions of how do you scale whatever solution you've developed to a network-wide scale, and then make it robust to changes in the applications and as well as in the network. So yeah, goes without saying, none of this work would be possible without the awesome set of collaborators I had, including my advisors at Georgia Tech, my mentors and colleagues at UChicago, as well as UCSD and AT&T. And thank you for patiently listening and asking wonderful set of questions. Okay. I can take more questions.
One quick question on your future reductions.
Yeah.
So you talk about internet, but particularly in a lot of Indian contexts, most of it is leapfrog using cellular technology, right? And so nobody really cares about having an internet at home per se. with the availability of cellular connectivity. And so, do you have a sense of how you would, like, imagine a future where there is no internet of the traditional sense?
You mean like fixed broadband, fixed
it's all
internet?
going
Yeah.
to be cellular broadband.
Yeah, yeah.
Right? So, how does your approach change? What do you need to do?
Yeah, basically, I mean, the architectures for these networks are different, and there are different sort of challenges, right? Fixed broadband, you probably don't have a lot of variability. It's mostly point connections, right? So the methods, how you analyze these networks would change. Some of them are all, I mean, depends on what questions you're answering. Some of them would remain same, but yeah, these networks bring different set of challenges as well. So one thing, for example, I mean, just to give a concrete example, we are looking at this Netrix platform that we design is currently designed for fixed technology, but can you add one like measurements for cellular or Wi-Fi connections, and then two, like how do you deploy, how do you make this platform say for when people are mobile, right? Like you cannot carry a Raspberry Pi, right? So one solution could be put it on buses and where you can wire it and then measure internet connectivity and those kind of things. So it, yeah, basically different challenges and different approaches.
We have two questions. One in the QA part, that was mostly TCP. So what about UDP?
I mean, basically, we're inferring QE for an application. So yeah, so it depends on what the application is using underneath. So now I think maybe what you're referring to is like streaming applications, for example, they are also now like they are UDP based. So for example, Quick is getting popular. Yeah, so while some of the mechanisms even for that are similar, I mean, you still have this chunk-based delivery, but there are some interesting set of challenges with Quick. Like you might be doing multiplexing, like since Quick has like more features in terms of doing multiplexing. So you possibly need to adapt these approaches as applications evolve and they start using different protocols. Yeah, and then we are doing it for video conferencing applications which are using UDP underneath. Yeah, I think the information available is different for UDP based monitoring versus TCP. TCP, you have a lot of like you can tell what like retransmissions, and you can also estimate RTT. So there are challenges of doing that with UDP traffic.
The device you made. So will it affect the network performance or even the privacy part? Like, can some application detect that there's a man in the middle there?
So this deployment is done as a sidecar. So you're not actually sitting between the user and the internet. So you cannot really see the user traffic, and it was essentially to get around these privacy issues. I mean, we were initially thinking of having a like man in the middle kind of deployment, but what we found, like people would ask like why I don't want to have something like that in my network, right? So the other issue you're referring to is like, let's say you do some speed test and then somebody's actually watching Netflix, right? It may impact user performance. Challenging to control for it. I mean, basically, there's not enough information to handle for that. But in a different setting of this deployment where we are actually doing browser-based measurements, you can tell whether the device is doing any transmission, and then you can you'll not do those measurements at those times. All right.
Thank you.
Yeah. Thanks.